speaker is Guanyan Li, and he'll be speaking about structural abstraction and refinement for probabilistic programs. Thank you, Guanyan.
Okay, thank you. Yeah. Hello, everyone. Good afternoon. I'm Guanyan Li. It's my pleasure here to present our work, which is co-authored by these authors. And in this work, we introduce new abstraction refinement methods dedicated to probabilistic program verifications. So I would first like to introduce the problem we studied, which is the probabilistic threshold problem. Well, so this symbol mimics the whole logic representation. And this triple, I think you have already known about, so I will abbreviate the explanation. So So ultimately, our interest is about to inquire if the violation probability is bounded by this threshold. And there are now many existing techniques to handle this problem, and such as program synthesis, predicate abstractions, and so on. And we would like to introduce a new framework called structural abstraction for this problem. So let's introduce an example to illustrate the problem more concretely, which will also be used throughout this talk. The program can be interpreted as a coin flipping game between the two players, and say Alice and Bob, and they make an initial toss, and if the heads down, then Alice wins immediately. Otherwise, Bob will choose a number of rounds, say C, to continue. And then Alice guesses that no heads-up will occur during this round. So the variable x then tracks this heads-down event, and Alice will win if the post-condition x equals 0 is met. So the violation probability means Bob is winning. And this probability of Bob winning is capped by 0.5 as C tends to infinite. So then we're going to introduce the core insights of this work, which stems from a non-traditional observation of the relationship between the probabilistic control-flow automaton and the Markov decision processes. Here, the PCFA is a common graphical model for representing the probabilistic programs. For this example, the program we just saw can be represented by this PCFA. So one of the most widely adopted relationship between the PCFA and MDP is that the MDP represents the semantics of the original PCFA. So more specifically, the state space of the PCFA. So for this specific example, the MDP will become something like this. So we first mark the locations in the PCFA to have a more concrete explanation. Then the program states of this PCFA are then tuples representing the locations, value of C and value of X. So for the initial state here, where the location is 1, then with some fixed value groups of C, then we can see here something C is 2, C is 0, or C is 5, and then with infinite number of X here. Then after the action of assigning X to 0 here, then we'll get to the location 2, where the X is fixed to be 0, and the C can continuing being any. And with other actions here, the 0 action here with distribution, and then we'll get either to the left branch that assigns C to be 0, or the right branch where it does nothing. And well, obviously, even for this very simple example, the semantics MDP is of infinite states as the initial value of C and X are unbounded. So instead of this former approach, we in this work propose a new relationship between PCFA and MDP called structural abstraction. So the insight is that the structure or the shape itself of this PCFA is very much like an MDP, like this. We can change this structure. So as compared to the original PCFA, where that the nodes in the, or the states in the MDP corresponds just to the locations back to its PCFA. And actions in the MDP corresponds to either the distribution tags, say the 0 and 1 here, and, or just simply the statements. But notably, now the statements are pure action labels without any computational semantics, as it's just MDP, which is emphasized with these angle brackets here. So instead of computation, they now becomes pure non-deterministic choices of the MDP. This is, I think, is an intuitive correspondence that it should be straightforward to observe. Every PCFA could have a unique underlying MDP via this way. Then back to our question, how does this insight help us with the probabilistic threshold problem? So the key is that the structural abstraction gives us an upper bound for the probabilistic violation probability. So let's first mark the pre and post condition here. And more specifically, let us mark these starting and ending states of the MDP. So the structural upper bound is just the maximum reachability probability of its underlying MDP, which means from this starting to this ending location, and this structural upper bound is now trivially 1. We then call this the structural upper bound of the violation probability. This should be a straightforward observation, as the transitions in the MDP are an over-approximation of the possible executions, safe or unsafe, of the PCFA. Namely, it considers simply all the possible traces in the PCFA regardless whether they are safe, unsafe, or even impossible to execute. So let's here consider some examples. Let's consider this trace. So I think this trace here, it becomes blue here. I think it's not that obvious. So this is surely a safe trace, as it assigns the x to be 0 and then get to the end without modifying anything. So, but this MDP may surely count this as contributing to its trivially 1 as structural upper bound. And we may even have this trace. Well, I think the color here is not that obvious. Yeah. This one is even worse because it is infeasible. Namely, there could not be any actual execution of this trace in reality. Notice this. So the C is assigned to be 0, and then it assumes C to be larger than 0. So this could never happen. And we call these traces the non-violating traces. Now that we know the initial structural abstraction is very coerced with a trivial upper bound of 1, and the reason is because the existence of these non-violating traces, it becomes natural that we simply can refine this structural upper bound by refining the automaton by eliminating more these non-violating traces. To this end, we introduce the principles of the structural refinement. The key idea is just to construct a new automaton here, denoted by V here, that simulates the violating traces of the original PCFA. Then by the standard automaton operations, the intersections in deterministic minimization here, we can establish a refined PCFA with the same violation probability as the original one, but with less non-violating traces. A notable point here is that the construction of V is totally irrelevant to the probabilities and can be done purely with the established non-probabilistic techniques. Namely, the V here, there's no probability. So to grasp this sense, we here present an example here. So this is the safe trace. We adopt the renowned technique of trace abstraction. So this involves the interpolation and the formation of the Floyd Hall automaton. We can first interpolate it. So this interpolation simply serves as a proof of why this trace is safe. That after x is assigned to 0, there's no statement to change this fact, and hence it will eventually become x equals 0, and hence it's safe. And then we form a Floyd Hall automaton from these interpolants by first merging the locations with the same proposition, like this. And then we can form the Floyd Hall automaton by adding all these transitions which the Hall triple from its source location to its ending locations holds. This forms the automaton Q1. And likewise, we can form a similar for Floyd Hall automaton for the infeasible trace. So here's the interpolation showing why it's infeasible. And then doing the similar things, we can get Q2 as the result. And then with the principles of the trace abstraction, we can construct V as the complements of the union of these two Floyd Hall automaton here. And notably, the above mentioned techniques are all standard and in the non-probabilistic trace abstractions and without any modifications. So by the principle, we can then obtain this refined PCFA that's within refined underlying MDP, where this absence branch becomes going to a place with an observing state here. Then this automaton will have the refined structural upper bound as 0.5 as expected, which is the exact upper bound, which is the exact violation probability. So then let us review the core benefits of this structural abstraction and refinement methods we just introduced. Then from the introduction, I think one could observe that our method reaches a clear separation between the probability and the semantics. On one hand, the structural abstraction itself does not need to care about the semantics, as every statement has been abstracted as the action labels and as non-deterministic choices by weighing the PCFA as MDP. On the other hand, during the refinement processes, the construction of V does not need to care about the probabilities. Specifically, if we review again the interpolation step, we can see that the probabilistic statements are treated as just skip statements, as they do not affect the logical reasoning of the program. Then we implemented our methods adopting the trace abstraction. As expected, our methods is more robust and generally applicable to a wider types of examples. We collected these examples from a wide range of literatures fairly and tested against some state-of-the-art tools such as Pro2 and Psi. And the experimental result shows that our tool handles 2 times more benchmarks against the state-of-the-art tools with higher efficiency in 73% of the cases. So in the interest of time, in this talk simply present the core idea of this work, and there are a lot more details and more contributions in the full paper. Specifically, to automate the principle, we provide a methodology using the CEGAR framework. So this CEGAR framework can automate the non-probabilistic verification techniques like the trace abstraction techniques. So with this, and we also optimize the trace abstraction techniques to reach the reputational completeness, which means the termination is guaranteed if it really violates the probability, the threshold. And also we will explain more thoroughly in the evaluation through all these, how we select the examples and how we analyze the results, etc. And I think this is all of my talk, and thank you. Yeah, I'm happy to accept any questions.
We've got time for a question. Well, I'll ask you a quick one. So what next? Where are you going next with this?
So hopefully you would like to add some, say, observed structure or something to reach the Bayesian something. Yeah, that's more popular, and we hope to extend it. Yeah, thank you.